Everybody's wrapped up there. So I want to just talk briefly about what your homework should be about. You probably need to get something you're going to want to write. I think you're going to want to jot this down. Not what's on the board just right here, but we're going to go through a couple of quick examples here. Our next thing up is the antiderivative gateway test. Okay, and so we've got this fundamental theorem part 2. It says that to find the area under some odd-shaped curve, one of the ways to do it is fundamental theorem part 2. Get the antiderivative. Get the antiderivative. Plug in B. Plug in A. Subtract. So obviously, getting the antiderivative would be a good thing to know how to do. So we will spend most of next week working on various antiderivatives. Now, the thing that you already know a little bit about antiderivatives is they're a little harder than derivatives from the sense that we've got this set of rules for derivatives. You know, if we get a product or a quotient, we got a rule to handle that. If you got a function inside a function, we got a rule to handle that. We got a rule for every one of the basic functions, what its derivative is. So on number 1 up here, actually I'll do these backwards. On number 2 here, we learned the power rule, and then we learned that if you have a 5 sitting inside there, that would squeeze the slope. I don't know if you remember that. Squeeze the graph, make it steeper. So you got to kick out a 5. And so we talked about how bring the 4 down, leave that alone, drop that to 3, kick out the 5. Okay, and the 5 and the 4 make 20. There's your derivative. But then we got into these ones with x cubed. How do we handle that? Well, we had this thing called the chain rule, right? The chain rule said do the derivative of the outside, which is cosine, leave the inside alone, kick out the derivative of the inside, the 3x squared. So, of course, some people think, well, if you're doing an antiderivative, maybe you just do the opposite. Of course, it does work with a constant. We've talked about how an antiderivative here, when you do the antiderivative of this, you'd raise that up to a 4, divide by 4, and you'd kick out a what here? Since there's a 5 inside. A 1/5, right? So some people carry that over to this and think, well, then I bet that would work on this one. You'd kick out a 1 over 3x squared or something. Well, it turns out that doesn't work. And of course, we know it doesn't work because anytime you do an antiderivative, to check it, you should just do the derivative of it, see if you get back to what you started with. Okay? And it would not work. So anyway, I've got these 2 derivatives worked out here. So now the thing is, okay, what about antiderivative? Well, it makes sense that if this is the derivative here, then if we do the antiderivative of that, it should give us this. Now notice my notation. I've used the integral symbol here with no numbers on it. That's the indefinite integral. Okay, the definite integral is the integral from a to b. That's a number. That's a fixed piece of area, the definite integral. An indefinite integral is different. That's just the antiderivative. That's notation for just antiderivative. So in your homework, you'll see problems look like this. What they're saying is just do the antiderivative. That's what that's saying. Okay, well, I've put this one down here. Of course, we know, since we just did the derivative of this and got that, we know the antiderivative of that is that. But how in the world would we know that? Right? I mean, how in the world would you start with this? You might look at that and say, oh, that's a product. There must be a product rule for antiderivatives. Well, no, there's not. Okay? Another thing you might notice is whenever you do a derivative, the answer always seems to get messier than what you started with. Would that be true? Think about the derivative test, the gateway test. You know, your answer was a lot messier than the original problem. Well, it kind of makes sense then if you're going backwards, the antiderivative, it almost would seem that your problems would get less messy, right? That your original problem would start out messy. When you do the antiderivative, would be less messy, and that's a little bit true on these. You look what you started with and what the antiderivative ends up being. Or again, the antiderivative of this would be this. So what we want to talk about today then is how in the world could we have been given these 2 problems, told to do their antiderivative, and been able to figure that out. Okay, so let's do it. So let's do this one over here first. Now, on these 5 little short homework problems that you have, we're going to use this method. It's called the U substitution method. The U substitution method. What you'll find out in antiderivatives is we don't have a bunch of rules. We have a few techniques that what they allow us to do is simplify the integrals so that we can do their antiderivatives. I showed you on page 333 that short list of antiderivatives that we need to know. That's the whole list. Our job will be to get any integral we see to turn it into something that looks like something on page 333. One of the techniques we'll have is called U substitution. Now, the hardest part of U substitution is, number one, knowing you're supposed to use it, and number two, figuring out what let U equal. Well, on this first homework problems, they're just going to tell you what to let U equal. As we get better at these, you'll start to figure it out yourself. Here's what we're going to do. So I want you to write that down. We're going to let U equal x cubed. We're going to let U equal x cubed. Now, why? Well, it's on the inside. You'll come to find out that one of the places you look, it's kind of chain rule in reverse, so the thing on the inside is going to be of interest to us. So we're going to let U equal x cubed. Now, the next thing we're going to do is a derivative of U with respect to x. Now, what's a derivative of U? And I'm going to write it this way, not U prime. Right? du dx equals what? 3x squared. Remember I told you when you do antiderivatives, we'll actually be doing some derivatives along the way? Now I'm going to do something that might seem kind of strange, but it's perfectly legal. I'm going to move the dx over to this side. I'm going to get du equals 3x squared dx. Like that. Now don't think about it as times or divide. Okay? There's a whole bunch of study about the differentials of how you can do this stuff. Don't worry about it. Matter of fact, from here on out, we're not even going to do that step. We're just going to skip right over that step. We're going to say, okay, we're going to pick a u. Then we're going to do the derivative of both sides, and we're just going to call this side du. Think of it derivative of u if you want. And then this side we do the derivative, and we have to be sure to tack on the dx. Again, why is the dx there? Well, it really came from this step. We moved it over. But there's no need to write that step every time, so I'm not going to. Okay, so we'll normally just do this. Okay, now, just like the name implies, we do a substitution. We're going to write ourselves a new integral, and we're going to take the stuff that's here, the x stuff, take it out, and put u's in its place. So, and I like, on the beginning of this anyway, I like to circle stuff. What can I put in the place of that right there? What would be equivalent to cosine x cubed? Cosine of u, right? I'm not doing antiderivative or anything here. I'm just substituting. So I'm taking cosine x cubed out, and I'm replacing it with cosine u, because u and x cubed, I said, were equal, right? Okay, what about this stuff that's left? The 3x squared and the dx. 3x squared and dx is equal to du. So what I've done is I have accounted, and that's very important when I do substitution. I have to account for everything that was in the original has to get transferred, substituted into my new one. Everything has been accounted for. Well, now look, that's an easy integral to do. I need the antiderivative of cosine u. Du means with respect to u, right? And so that's a very important piece of this. Well, what's the antiderivative of cosine? Sine u plus c. And what do you suppose I do at my last step? Substitute the u back out and put the x cubed in its place. And I get sine of x cubed plus c. And if you go back to the other page, sure enough, that is exactly what we said the antiderivative should be. So when you look at that, you say, well, that is not so bad then. In other words, the antiderivative itself wasn't bad to do, but it was the process of turning the integral into something that I could then do the antiderivative of. Okay? So, let's do this one. What do you suspect you're going to let u equal on this one? 5x plus 2. Now, you're going to come to find out as we do these that a lot of them you're going to say, hey, let's try u equals this. Oh, it doesn't work. Well, let's try something else. And you're going to get better through practice of what to let u equal, or if you're supposed to use u substitution, whatever. Okay, next step is to write du. Du means a derivative of that would be what? 5 dx. Don't forget the dx. Okay? Now, we're going to make a substitution. All right, so for this, I'm going to replace that right there with what? What's that right there? U cubed. That's u cubed, right? Now I got this 20. What do you suppose I'll do with that 20? Yeah, remember how we said we can pull it out in front? So I'm not really even going to substitute it out. I'm just going to bring it on down, and I'm going to pull it out in front, right? Wouldn't have had to put it in front, but We can. We know that. So the 20 doesn't get substituted out. It's a 20. It stays a 20, whether you're using X's or U's. Doesn't matter. So, but I still have to see. Now, some people would be tempted to quit right there, and that'd be wrong. Because I have, and this is why I like to circle things. I have not accounted for the dx. Right? I have not substituted out the dx. So what is dx equal to? Yes, it is perfectly legal, and I don't want to do du over 5 because then that gets confusing. I think it's 1/5 du would be better. We absolutely will do that sometimes with that du equals dx. 5dx, we will divide that over. Dx is equal to 1/5 du. So I'm going to take the dx out. Now the 1/5 is a constant, so we usually stick it out in front. And the du, of course, we know that always goes on that far right end. The dx or the du is always way out over there. So I'll put the 1/5 in front, and I'll put the du there. So look what I got. I got a 1/5 and a 20. Of course, that makes 4. And now I'm going to do this antiderivative. You see what I've done? I've turned it into a very simple one to do. I want to do the antiderivative of u cubed, which is what? 1/4 u to the 4th plus c. Of course, the 4 and the 1/4 cancel. And then I can go ahead and substitute my x back in. 5x plus 2 to the 4th plus c, which, again, going back to the other page, is exactly what we thought it should be. Okay? That is called u substitution. It's really, in a sense, the chain rule in reverse. It's something that is most useful when you have stuff on the inside. So that's a key piece of it to look at. But it also is used in some other cases too, not just stuff on the inside. And so we'll learn all the different variations of u substitution, all the different things that can pop up. And it takes a lot of practice because there are a lot of different things that pop up along the way. And so as we practice those, we'll run into, yeah.
So when you do the antiderivative, you can just get rid of du?
Okay, that's a great question. When you do the antiderivative, like of this u cubed, the du just disappears. What happened to it? Well, I would argue it this way. When I tell you to do the derivative of x to the 4th with respect to x, what do you write? 4x cubed. What happens to this? It just goes away. In other words, this was just saying do the derivative with respect to x. That's what you did. This is saying do the integral of u cubed with respect to u. That's really all the du is doing there. So yes, when you do the antiderivative, the integral symbol goes away. The du goes away because they were just there telling you do the integral or do the antiderivative with respect to u. So yes, they just go away. Okay, so 1 through 9 odd, 5 little problems. They give you the integral. They tell you what to use for u. So all you need is to do the du part, substitute it out, and do what we did there. See if you can get that to work for you. Okay, it's a pretty short little assignment, but it'll give us a running kind of a head start on Monday, so we can have more work time.
No, engineering, imaginary numbers are J's.
Yes.
Here, imaginary numbers.